Hello and welcome to the Kavli Foundation Spotlight Live webcast on stellar explosions, death dances, and the life of stars. Recently, astronomers witnessed the biggest burst of energy ever seen from a dying star. It was nearly 50 billion times more intense than visible light. In another discovery, astronomers found that a well-known pair of stars orbiting one another is actually our earliest view ever of one star devouring its companion in a dramatic death dance. These are fascinating discoveries, but what do they tell us about the birth and death of stars? And what might they reveal about the evolution of the universe? My name is Bruce Lieberman, and I'm joined by two people who can answer some of these questions and more, including questions from you. Nicola Omodei led an analysis of the star explosion that I told you about. He's from Stanford University, where he's an associate member of the Kavli Institute for Particle Astrophysics and Cosmology. Norbert Schulz was key to the second discovery, that pair of stars in that death dance I told you about. He led observations for this pair of stars, and he's a research scientist at the Kavli Institute for Astrophysics and Space Research at MIT. Nicola and Norbert, thank you so much for joining us today.
You're welcome.
Good morning.
Great. Thank you. Well, let's begin with a brief slideshow. Right before the holidays, astronomers announced discovering the biggest burst of energy ever seen from a star, a burst that had traveled for about 3.8 billion years before reaching our space telescopes. Here should be an artist's depiction of what that may have looked like up close. Coming next is an illustration of that binary star system that I mentioned earlier, our earliest look yet of an exploded star devouring its companion. Astronomers found that this pair 43 years ago, but now we know that this is the youngest of its kind ever found, only about 4,600 years old. For this kind of star system, that's just moments after it was born. So, what are these discoveries telling us about the universe that we didn't know before? And what do they reveal about the life cycles of stars like the ones in this image? Let's find out, but let's also get to your questions. If you have any, please send them to the Kavli Foundation over email, or you can send them over Twitter using the hashtag KavliLive. Okay, Norbert and Nicola, let's start with a couple of basic questions. I'd like each of you to talk about what these two latest discoveries together reveal about stars and the universe in the broadest sense. Let's start with Norbert.
Well, just the fact that stars engage in evolution and life cycles, I think, sends a message about what the universe is about. We want to know where we come from, how we're made of. Life cycles of stars determine the elements and their abundances, for example. So we know how much iron, how much lead, how much gold we find on Earth, and why we find so little hydrogen, so little lithium, and so little helium. And so, what is our fate? Our fate of the Earth, the solar system, and the Sun? I think those are very fundamental questions we have.
Nicola, would you like to add to that?
Yes, I also like to mention that, of course, our study and our work is driven by the curiosity of how the universe works. And the case of an explosion of a very massive star, it's giving us the opportunity to study the physics in this most extreme condition. In fact, think about a star that lives a billion of years, and in a few seconds and minutes collapse and give rise to a very powerful explosion of gamma rays. So in this short blink, with respect to the whole life of a star, we can study physics in extreme condition of gravity, and we also have a fantastic laboratory to study how particles are accelerated. Something that you cannot do at Earth, for example.
Okay.
Kind of like also tells us there's one driving force in the universe, and that's gravity. Gravity drives most of the most energetic processes we observe. And I think that is unusual for us on Earth, There's an example on Earth. I mean, if you go to hydro power, that's how we draw energy from gravity. The universe does it on a large scale.
So I'd like to ask you both again, however, and you may have talked about it a little bit already, but both of these phenomena signal the end of stars, the end of something, but also the beginning of something new. So my question is, do these stars or the stuff that makes stars ever really die out? Nicola.
So, well, what we observe when we see a gamma ray burst is indeed the death of a maxi star. So at the end of their life, massive, highly spinning star collapse, and that's also why what Norbert was saying, the gravity is really ruling this process. Collapsing, you form jets of material along the poles of the star, and matter can accelerate it to speed which is very close to the speed of light. So what you see is the interaction of this matter along the jets. You have what we think are internal collisions or internal shocks of shells of matters. During these shocks, particles are accelerated, and you see with the telescopes such as Fermi, you see the radiation coming to the Earth. What is left after is a black hole, a massive black hole at the center of this object. So it's true that is the end of a star, is an explosion phenomena, but yet you are left with a black hole. So it's a new object which is sitting at the center of the previous star.
Norbert, what's amazing to me is that we have these these exploded stars, and the remnant is very, very small, whether it's in the object that you study or the one that Nicola studies, and yet we have these tremendous amounts of energy from something that's very, very small. And I was just wondering if you could talk about that, about why that's the case.
Well, at the end, if I reminisce a little bit on what has been said, sure, I mean, it's the end of a life cycle and the beginning of a new cycle. But at the end, if you go for the star, it's just a plain transition. Because all that happens is that at some point, the star just does not have enough fuel to counter gravity based on, say, fusion of matter. Once that is gone, it transitions into another phase. It explodes, and what's left is what we call a compact object, which is then, of course, fueled and stabilized by different types of forces. It's still the star, it's just a little bit leaner, and it's governed by different forces that count as gravity. Again, in the case of, say, a neutron star, we have nuclear forces now taking over the interior of the star and making it a stable object. And
Norbert,
so,
let me stop you right there.
Yeah.
Tell me, let's back up a little bit and tell me what a neutron star is and where it fits into the phenomenon that you were studying.
Well,
kind of start from a little earlier in the process.
Yes, there are several stages of what happens after a gravitational collapse. Thermal energy, of course, cannot work anymore because there is no fuel, so it has to go into the next stage. So matter gets compressed and compressed, and at some point electrons take over, and electrons provide a form of pressure against gravity. Now, sometimes it just pushes further in, and gravity is just so strong, collapses further. Then even electrons cannot counter that type of force. Then it goes into the nuclear domain, and then what we call neutrons that have a certain nuclear force can counter gravity again, and it comes to another halt. That is the stage we would call a neutron star. Now, we have to realize, I mean, there's a lot of big objects in the universe, but size does not really matter so much. When we talk about gravity, at the end, mass is what's matter. And in this case of a neutron star, it's size and mass. And so, since we have this incredibly dense star, you have to realize a teaspoon of a star like that weighs like an air carrier.
Really?
So
wow.
And so, of course, imagine how much the gravity is increased if you come close to such an object. And that's what you see happening in, for example, in these X-ray binaries that are too close to a neighboring star and then just suck the lifeline out of the star.
So Norbert, let's stay on your discovery for a moment. So tell me what this phenomena is that you studied, this pair of stars where one is devouring the other. Kind of tell me briefly how that forms, and then what was new about your particular discovery. And then we're going to go to Nicola.
Well, in general, what we study is what we call X-ray binaries. X-ray binaries, since its discovery in the early 1960s, actually the very first X-ray source in the sky, extrasolar X-ray source, was an X-ray binary, are the most powerful X-ray sources we know. I mean, you have to realize these are sources that generate X-rays that are 100 billion times more than what the sun can produce. And they do that on a persistent basis. And so what we have here is that in an incident, we have a compact object in orbit with either a normal or a massive star. And the gravity of the compact object is just accreting matter from its companion. Now that matter, as we just heard, has to go through the entire gravitational potential of the compact object. And at some point, when it just falls through that potential, it gets released in the vicinity of the neutron star, and the energy that it's released is so strong that we have this high luminosity of X-rays. And so,
Norbert, where can we find this binary star system in the sky? It's in the southern sky, right?
It's in Circinus. It's in the southern sky.
Okay.
Almost right in the middle. You can actually not see it by eye because it's way too far away.
And how far away is it?
It's about 7 kiloparsec. So if we do in light years, it's over 20,000 light years away.
Very, very far away. So did this system start as two normal stars orbiting each other? They just happened to be close to each other, and then one of them blew up? Is that what happened?
Well, in a nutshell, that's probably what happened.
Okay.
Now,
and the one that blew up turned into this neutron star.
What kind of stars we are talking about, that's of course a completely different puzzle. Of course, we know that in Circinus X1, the compact object is a neutron star. We know that because we observe fingerprints of a neutron star. In this case, what we call type 1 X-ray bursts, which are fingerprints of thermonuclear explosions that can only happen on a neutron star. We know that from calculations. And so we know it's a neutron star, so its progenitor probably was a massive stars between 8 and 25 solar masses. These tend to generate neutron stars.
Much bigger than the sun.
Much bigger than the sun. There's one other scenario we can think of, and that is actually what we call an accretion-induced collapse of a white dwarf. The reason why we don't believe that's the case, we don't see post-mortem signatures of it. And so we do believe that the progenitor was just a massive star producing a neutron star.
Okay.
That's why we see, that's why we see the supernova remnant. We were looking for this for a long, long time. And that's part of the discovery.
Okay. Nicola, your discovery was, as I said, the most intense explosion associated with a dying star ever seen. Is that right? Tell me about this and where this object is from.
Yes, so I think the most interesting thing of this object is that it was extraordinarily close to us. In fact, the kind of object I'm studying, so gamma ray bursts, are originating from high spinning, rotating, massive star far away from us. Typically, they are 10 billion light years away. So this means that these objects has to be extremely bright, and in fact, we know that the energy that this monster releases about in gamma rays is about the mass of the sun converted in gamma rays in a few seconds. So
Nicola,
yes.
Gamma rays, so these are called gamma ray bursts, is what these explosions are called. And gamma rays, explain to me real quickly for our audience what gamma rays are.
So gamma rays are basically light, but with a much higher energy, or much shorter wavelength, or much higher frequency. As you mentioned before, they are about 50 billion times higher than the visible light. They are light. They come to us as a flash of light. You just need a different telescope to detect these lights, and that's why we need to put a telescope in orbit, such as Fermi, because the atmosphere naturally shields us from gamma rays. So you have to put telescope around in orbit around the Earth to detect these objects. So these objects are extremely bright, but also they are very rare in the universe. That's why you need to go and look farther away, because you have a larger volume on the universe if you go farther away. The peculiarity of 130427A is that it was very close to us. You mentioned already this before. It's about 3.6 billion light year, which is yet far in our common understanding. The light takes 3.6 billion years to reach to us, but in the context of gamma ray burst, was extremely close to us. So this means that for the first time, we were able to really see details that we weren't able to see before. So if you think about the tip of the iceberg, this GRB was a completely new layer of ice that we were able to see. And
were we able to find out more details because it was closer to Earth than most gamma ray bursts are? Is that why we were able to find out more details about exactly what happens?
Yes, mostly yes. And also because it was extremely bright. So we had close bursts in the past, but they were typically much less brighter intrinsically. So the resulting flux that we were detecting was not as bright as the 130427A. This particular burst was bright, intrinsically bright, comparable to the, let's say, top 5, top 10 GRB that we have ever detected, but was incredible close to us. So the resulting flux was way more powerful than any other bursts.
Let me ask a question for both of you. Now, we're both talking about the explosion of stars and what comes after. Can we have a burst of energy during an exploding star, a gamma ray burst, that is then followed by the formation of an X-ray binary if one of the stars that explodes is paired with another one? In other words, can you have two phenomena in the same place? Norbert.
Generally, I wouldn't say no to that. If the system or if the second companion survives the explosion. See, that's always the big problem. Of course, although even in a gamma ray burst, the explosion is confined to a single star, it can have a companion. The question is, these explosions are huge. They are so energetic that the likelihood that any companion that was associated with the star might survive or survive the binding is very unlikely. It will be just kicked away.
That's right, Nicola. What do you think? That's very unlikely. I mean, the GRB, the gamma ray burst is so energetic that even if there was a companion, it wouldn't survive the explosion.
Yes, I would agree with that. Also, there are some observational evidence. If you just think of the numbers, most of the X-ray binaries we found are in our galaxy. We see X-ray binaries also from other galaxies, but we cannot see X-ray binaries as far as we see GRBs. So the two population underlying of stars, the two population of stars are really different. So one tends to be closer to us, the other one is definitely not local. So it's observation also is telling us that these two objects are not really related one to each other.
Well, let me ask you both this. I mean, both of these phenomena seem very dangerous if you are close to them, as we've just discussed. So, are we just lucky that neither of these phenomena are situated close to Earth? And what's the likelihood that one of them could form close to our solar system?
Well,
Norbert.
Well, we do know what we call the solar neighborhood pretty closely, and fortunately, we also know that massive stars are far enough away. Even the next massive star that could form what we call supernova explosion is far enough away not to be really a problem for us. So the answer is no, we don't have to worry about it.
And Nicola, could we potentially get a gamma ray burst from within the Milky Way galaxy, some star that's very old and massive star that's about to explode?
Okay, yeah, that's an interesting question. So first of all, as I mentioned, GRBs are very, very rare phenomena. We have to look 7, 10 billion light years away to be able to see them. So if you do some, let's say, back on the envelope calculation, taking into account the rate of GRBs that we are observing and the fate of massive stars and the rate of massive stars. So I would say that there are few GRB per galaxy per million years. This is just an order of magnitude. But then you also need, in order to be dangerous for Earth, that the GRB jets points toward the Earth. And this, again, decrease the probability to have one of these GRBs pointing to the Earth by a factor of 100 or even more. So there are some speculation in the field, and some, I would say, small group of scientists also suggested that some of the previous mass extinction event happened 100 million years ago could be due to powerful GRB in our own galaxy.
This is before the extinction of the dinosaurs, which is, of course, thought to be caused by an asteroid. So this would be 100 million years ago, as opposed to 65 million years ago.
Exactly, and there are no evidence for this. So it's just an hypothesis and a speculation. So it's very unlikely that in the lifetime of the Earth we could witness another GRB.
So, Nicola, I'm sorry, Norbert, why don't you, if you wanted to say something, and then I had a question for Nicola. Norbert.
Well, you have to realize gamma ray bursts in the early 70s almost made it into a political controversy, the way they were detected, because you have to realize back in the days there was the SALT Treaty for observing nuclear events on Earth, and so there were satellites, the Vela satellites in orbit, and they were recording gamma ray bursts, which were signatures of nuclear explosions on Earth, but there were none. And so if scientists wouldn't have realized very quickly that these are from outer space, they would have actually constituted a violation of the SALT treaties, and we would have had a political situation here. So,
Interesting. It was something totally from the cosmos.
it's totally from the cosmos, and influencing our life on Earth here.
So, Nicola, let me ask you. So, if you can answer very briefly, why are gamma ray bursts more common the farther away they are? Is that just because there's more of them in time farther away?
So I would say that is two effects that contribute to this. So first of all, it's the rate of massive star creation. So we know that in the past the universe was more active, producing stars. So what we call star formation rate was higher in the past than it is now. When you create a bunch of stars, you tend to create the most of the star with a mass around 1 solar mass, but you also create few stars with a large mass. The massive stars are also the one that die before, so they last fewer time. Shorter time, and this is because they are so massive that the gravity cannot. The gravity is quickly burning all the fuel, so the fuel cannot keep up with gravity. So massive stars are the first stars that are dying right after they are created. So the rate of gamma ray burst, which is basically tracing the rate of how massive stars are dying, is also tracing the rate of how massive stars are created. So what we know is that, and what we observe also is that GRBs are typically events that happen back in time or far away, which is a synonym.
Okay, Norbert, I'd like you to summarize briefly because we're actually coming to the end. We may go a minute or two over to cover this, but this X-ray binary that was discovered back in 1971 is emitting all these X-rays. It's very hard, very difficult, very bright. It's very difficult to find out what's going on close in, but in the mid-2000, 2005 or so, is that right? That it started to dim, and this is why you were able to find out some new things about this system. Tell me what you found out that was new.
Well, we know since its discovery, and we looked at this source since 1971, and so we have almost 40 years of coverage of the source. And we've seen it back in the early 80s from being very faint, going up to the very brightest source in the sky, and now coming back to a very faint state. And so it has the unique possibility to change its luminosity on a grand scale. Not all X-ray binaries can do that, and we're very puzzled about why this would actually happen. And to be quite honest, we still don't really know. Of course, the fact that it dimmed provided an opportunity for us, because in that respect, the light bulb goes out and you see the background. And only in the background is a much dimmer object, and that a much dimmer object is kind of like the echo of its creation, what we call the illumination of the supernova remnant. Now, we were always puzzled about not only the violent behavior, but it has a highly eccentric orbit. We have to realize it only connects with its companion star for about 15% of its orbit. Otherwise, it just floats free in the sky. That's highly unusual. And so it behaves like a Lomas X-ray binaries. These are sources we know are very, very old. But it has other behaviors that reminded us that are completely unique. Now, finding the supernova remnant and dating the supernova remnant told us that no, this is actually a very young system. Now, of course, that puts us completely at odds with a lot of what we know about the source, but it does explain why we have such an eccentric orbit. It hasn't circularized yet. So over time, the orbit will mellow down and will become more stable, and all these hiccups will cease out. The fact that that hasn't done yet actually is a clear sign of youth, but it never exhibited any signs of youth. This is the first time we can actually, with a very, very high probability, tell its age. Yes, it's young. And of course, as much as we're happy about that finding, as usual, it solves the problem, but it creates many more we haven't even thought about, because now we have to explain the other behavior in the framework of a young system. That's not going to be easy.
So those are your next steps in research on this particular object?
Definitely.
Okay, Nicola, one of the major findings of this gamma ray burst was that you really were able to find out that this burst gets gets its peak energy far from its point of origin. Did I phrase that correctly?
I think yes. So there are two things. One, what we were thinking before this GRB was that the acceleration of particles, which is where basically the highest energy gamma ray come from, was at the so-called external shock. So when these jets interact with the interstellar medium far from the star. What we learn from this GRB in particular is that we had events with an energy higher than what we previously expected. So we were in our model we were thinking that gamma rays were produced by the so-called synchrotron emission, and if you work out the equation, you also find that there is a limit at which the synchrotron emission it becomes too efficient in order to accelerate particles. So
explain to me what synchrotron emission is.
It's a well-known physical process. So when a charged particles interact with a magnetic field, it emits radiation basically. And if the energy of the particle is high enough, this radiation can eventually be in X-rays or also gamma rays. But in order to have this high energy radiation, you also need to accelerate the particle. So you have a balance between the time you need to accelerate a particle and how fast the particle lose radiation by synchrotron emission. And before this GRB, we thought that in GRB we could see a synchrotron radiation up to 10, probably 30 giga electron volt, while with this GRB we were observing energy up to 100 giga electron volt, and this somehow violate and put a strong constraint on the model and challenges actually the model that we were thinking for GRBs.
So this process that occurs as the energy leaves the exploding star, the process that you thought limits how bright it can be, it actually can be a lot brighter than you thought it could be.
Yes.
A lot more energetic.
Well, I would say that the way particles are accelerated in GRB has to be more efficient. So there must be a way to accelerate particle quicker than what we thought, or you also have to go back and rethink about all the approximation you have done working out these models and refine the details in order to fit coherently all the observations. Okay.
As we wrap up here, I would just like each of you, starting with Norbert, just to tell me what your biggest question about this X-ray binary. What's the biggest kind of open question regarding this? And then I'd like Nicola to talk about the biggest question regarding the gamma ray bursts. Norbert.
Well, this just concerns what I did when I started out looking for X-ray binaries. And that is very, very simple. I mean, we know the basic physics, how it generates its energy, but we still don't know how it generates its radiation and its radiation variability, and how this feeds back into the accretion process. And so one of the next studies will be, now that we know, well, it's a young system, it might be a massive companion, to test a few different models about the accretion process and see whether they fit. And of course, we have to do a few more observations that are probably phased to do so. Well, it's going to be a stretch.
Okay, and Nicola, it's further studies about how the gamma ray burst can get its peak energies, how and where.
I think yes. I think that the big question is how particle can be accelerated to that high energy during a gamma ray burst, and I think this will help us to understand the process that are taking place in these monsters. We were thinking for decades now about shock acceleration. Is that really what it is? Is this observation challenging one of the, let's say, concept that we were taking as certain shock acceleration? Maybe we have to invoke other way to accelerate particles, or is really the synchrotron emission the responsible of high energy gamma rays that we are observing? So I think that it's nice to see how a few observations, and hopefully there will be more and more, can really challenge well accepted models, and could potentially drive towards other models and our explanation. So yeah, I think that the particle acceleration is really the open question.
So exactly how these gamma ray bursts, these huge bursts of energy, reach the energy levels they do is still an unsolved question. The
Yes.
details of that. Yeah. Okay. Well, Norbert and Nicola, I want to thank you very much for joining me today. I think we've had a great discussion, and I want to thank our viewers for watching too, and for sticking with us for an extra couple of minutes to cover some extra and important questions. Thanks a lot, Nicola and Norbert, again for joining me.
You're welcome. Glad to be here.
If you'd like to see this webcast, it will be available almost immediately at the Kavli Foundation website. And if you'd like to learn about future webcasts, please follow the Kavli Foundation at its website again, and also on Twitter. Thanks again for watching, and we will see you next time.